400 watt-hours per kilogram, 800 to 900 watt-hours per liter, charging from 10 to 80% in just over 10 minutes. No fire when punctured. If these numbers are real, why aren't solid-state batteries already everywhere in electric vehicles? And if the answer is still not ready, then what exactly are they not ready for? Range, cost, lifespan, or the way we are fundamentally misunderstanding the future of EVs? On paper, solid-state batteries look like they were born for electric cars. With an energy density of 400 watt-hours per kilogram, a battery pack of the same weight could extend driving range by roughly 40 to 60% compared to today's lithium-ion packs. A mid-size electric sedan using a 75 kilowatt-hour pack today could theoretically exceed 900 kilometers of range without adding any extra mass. In terms of volume, 800 to 900 watt-hours per liter gives automakers a choice: push range even further, or keep range constant while shrinking the battery pack. That frees up space for a larger cabin, improved aerodynamics, or stronger crash structures. This is exactly why solid-state batteries are often described as the key to the next generation of EVs. But once solid-state batteries are placed into real electric vehicles, those expectations collide head-on with the harsh realities of automotive requirements. EVs don't just need high energy density, they need long life. Most automakers target more than 1,500 to 2,000 full charge cycles, equivalent to over 300,000 kilometers of real-world driving. Under these conditions, the biggest weakness of solid-state batteries emerges: rapid degradation under high current and changing mechanical pressure. A solid-state cell can look impressive after 200 to 300 cycles, but to meet automotive standards, it must remain stable for thousands of cycles while enduring vibration, temperature swings, and frequent fast charging. Very few current prototypes have cleared that bar. Fast charging, a core part of the EV user experience, further exposes the gap between theory and reality. Yes, solid electrolytes reduce fire risk and theoretically allow higher charging currents. But in an EV, fast charging doesn't happen a handful of times. It happens hundreds of times over the vehicle's lifetime. Repeated high current charging places enormous stress on lithium metal anodes, accelerating dendrite formation and capacity loss faster than expected. The result is a paradox that EV buyers would find hard to accept: extremely fast charging in the first year, followed by noticeably faster degradation in the years that follow. Safety in electric vehicles is also more complex than simply not catching fire. EV battery packs must survive crashes, chassis deformation, and continue operating reliably after minor impacts. Solid-state batteries may not ignite when punctured, but they are more prone to internal contact loss after mechanical deformation. A battery pack that doesn't burn but suddenly loses power or develops localized resistance increases is not comprehensive safety. It's a new and less predictable risk. For automakers, that trade-off is far from trivial. Cost is the factor that most clearly pushes solid-state batteries away from the vision of mass-market EVs. Electric cars cannot rely on the best technology alone. They must rely on technology that is good enough at a price the market can accept. Today's commercial lithium-ion batteries are approaching a cost floor, with global average pack prices around $100 to $120 per kilowatt-hour, and even lower for LFP in major markets. This milestone reflects more than 30 years of optimization, high manufacturing yield, and a mature supply chain. Solid-state batteries, by contrast, are starting from a completely different position. Technical estimates suggest early commercial solid-state cells could cost roughly $200 to $400 per kilowatt-hour, depending on electrolyte chemistry and manufacturing methods. The issue is not a single expensive material, but the entire system: ultra-dry manufacturing environments with humidity measured in parts per million, high-pressure stacking to maintain solid-solid contact, strict quality control, and low initial yields. Even a drop in yield from 95% to 80% can cause cost per kilowatt-hour to surge dramatically. This explains why, if solid-state batteries appear in electric vehicles in the near term, they will almost certainly debut in luxury cars, high-performance electric sports cars, or limited production models. In these segments, battery cost is a smaller fraction of the vehicle's total price. For mass-market EVs, where the battery can account for 30 to 40% of vehicle cost, any technology that hasn't solved the cost equation simply cannot scale. In other words, solid-state batteries are not held back by a lack of technical potential, but by a very practical barrier. They are not cheap enough for the masses. In the United States, no electric vehicle sold to consumers currently uses a solid-state battery. Not Tesla, not Ford, not GM, not Rivian. Every commercial EV on the market still relies on conventional lithium-ion chemistries such as NMC or LFP, with proven lifespans of 1,500 to 3,000 cycles, equivalent to 300,000 to 500,000 kilometers of real-world use. This is the baseline the U.S. market expects for long-term warranties. This does not mean the U.S. is lagging technologically. It reflects extremely strict standards for durability and legal liability. A battery pack sold in the U.S. must tolerate temperatures from -30 degrees Celsius to above 50 degrees Celsius, endure thousands of hours of vibration, and retain at least 70 to 80% of its capacity after 8 to 10 years. Under those criteria, most solid-state batteries simply do not yet have enough long-term data to pass the gate. Solid-state batteries do exist in the U.S., but only at the prototype and test vehicle level. BMW and Ford, through Solid Power, have integrated sulfide-based solid-state cells into experimental battery packs. These cells reportedly reach 380 to 400 watt-hours per kilogram, higher than today's commercial lithium-ion batteries at around 250 to 300 watt-hours per kilogram. The vehicles drive on real roads, but these are engineering trials, not customer products. The critical missing piece is cycle life, which has not been publicly disclosed. In the battery industry, a cell that cannot reliably exceed 1,000 cycles has virtually no commercial value for EVs. Many solid-state batteries today remain stable for only a few hundred cycles under controlled conditions. Mercedes-Benz in the US is also working with Factorial Energy to test solid-state batteries in premium EVs. Factorial claims volumetric energy densities of 800 to 900 watt-hours per liter and 10 to 80% charging in roughly 10 to 12 minutes under ideal conditions. The cars are driving on public roads, but Mercedes describes this stage as validation, not pre-production. In other words, performance has been demonstrated, but long-term durability has not.